In this video, we're going to work some problems to review for Chapter 7. So you can use your worksheet 7.3 on these. So here, because we have an odd power of cosine, we're going to save one of those off. So we'll make that a cosine squared x, and then we'll save cosine x dx to use as a du ultimately. So we're going to commit to making the u equal to sine. So from our favorite identity, sine squared plus cosine squared equals 1, we know that we can trade in our cosine squared for 1 minus sine squared, which is what we're going to do here. And then we'll still save out this cosine to use as our du, and we'll distribute that. So that will become then the integral. We'll make it into two separate integrals. The integral of sine squared x with our cosine x dx, and then minus the integral of, I think that'll be sine to the fourth, with another cosine x dx. So for both of these, we'll make the same substitution, that u is going to be sine x, and so du will be our cosine x dx. So that's going to make this integral be u squared du, and this integral u to the fourth du. So we'll get 1/3 u cubed minus 1/5 u to the fifth, and then we'll go back to our u, which was sine. So that's going to be 1/3 sine cubed x minus 1/5 sine to the fifth of x plus c. So there's our first one. On the second one, we don't have any trig function with an odd power, so we're going to have to do our power reducing formulas here. And so we know that sine squared is equal to, sine squared is 1 minus cosine of 2x all over 2. So our integral will become 1 minus cosine of 2x over 2 squared. So when we square that 2 in the denominator, that's a 1/4. We can just pull that out. We'll get the first one squared twice the product plus the second one squared. So we can now separate the first two into their own integrals. So 1/4 of 1 dx, and then the 1/4 times -2 will make that a 1/2 integral of cosine of 2x. And that third one, we're going to have to, we have 1/4 the integral of cosine squared 2x. So we're going to have to do another power reducing formula use there. So the cosine squared of 2x will be 1 plus the cosine of double that angle will be 4x over 2. So this will then become a 1/8, and we'll have a 1 plus cosine of 4x dx. So putting that all together, we're going to get from here, we're going to get 1/4 x, and from here we're going to get a 1/4 sine of 2x, and here we're going to split this up. So from the first part, we'll get a 1/8 x. From that second part, we're going to actually get a 1/32 sine of 4x. So combining the 1/4 x and the 1/8 x, at the end of the day, we are going to get 3/8 x minus 1/4 sine of 2x, and plus 1/32 sine of 4x plus c. That's our final answer. Okay, let's slide up a bit here and see what we can do with this one. So we can pick off one of the cosecants with the cotangents to use as our du. So we'll leave the cosecant cubed of x, and then we can pick off one of the cosecants and that cotangent to ultimately be part of the du. So we're going to commit to calling u cosecant x, which we can, I guess, do right now. So we'll say u is going to be cosecant of x. That makes du a negative cosecant cotangent of x dx. And so our integral is going to become u to the third, and the du's will match except for we need an extra negative sign. So that will become a negative 1/4 u to the fourth, which will be a negative 1/4 cosecant to the fourth of x plus c. Okay. So on the next one, we have different angles here. So we have to look on our that 7-3 sheet and find our formula for cosine. So according to our formula on our 7-3 worksheet, the cosine of mx times the cosine of nx is going to be 1/2. I'll just pull that outside the integral. And then we're going to get the cosine of 2x minus 4x times, plus rather, plus the cosine of that sum. So that's going to be the cosine of 2x plus 4x. So we're going to get 1/2. Now from here we're going to get the cosine of negative 2x, but because cosine is an even function, the cosine of a negative 2x is the same as the cosine of 2x. So we can make that just be the integral of cosine 2x, and then we're going to get 1/2 times the integral of cosine 6x. And you can do a substitution if you need it, or if you can recognize it. This is going to be 1/4 times the sine of 2x, and this will be a 1/12 times the sine of 6x plus c. Okay. So next we're going to switch to this is going to require a trig substitution. So if we think about how we're going to label our triangle, I think this is always the trickiest part. Since we can think of that as being 1 over the square root of 16 minus x squared to the third. So because we have a square root of 16 minus x squared, we're going to put the 4 as the hypotenuse, and then we can either choose this side to be the x and this side to be the square root of 16 minus x squared, or we may have to switch those around. If we choose it this way, then to match the x with the constant, that would be opposite over hypotenuse. So we would get sine of theta is x over 4, which means x would be 4 sine theta, and that's what we want because we want x to be either a sine, a tangent, or a secant. So this is going to qualify. This is what we want. We need to figure out what the dx is. So differentiating that, we're going to get 4 cosine theta d theta. we need to figure out what that radical is. So we're going to connect the radical with the constant. So that means the cosine of theta will be the adjacent, which is our radical, over the hypotenuse. And that means that 4 cosine theta is going to be that square root of 16 minus x squared. So now we're ready to get our new integral. So we're going to say it's going to be the integral of the dx. We are going to call 4 cosine of theta d theta. The radical is going to be 4 cosine of theta, and that's going to be to the third. So it looks like one of those 4 cosine thetas is going to cancel. And that will get us to 1 over. The 4 will get squared and be 16, and we've got cosine squared theta d theta. So we can pull that 1/16 out, and 1 over cosine squared theta we would like to think of as secant squared theta, because the integral of secant squared theta is tangent theta. Then we have to go back from the thetas to our x's. So we go back to our triangle and see that tangent theta is opposite over adjacent. So that's going to be x over the square root of 16 minus x squared. So at the end of the day, it looks like we're going to get x over 16 times the square root of 16 minus x squared plus c. Okay, let's slide up and try this other one. That looks a little scary. Let's see if we can come up with our triangle and name our angle. So because we have a square root of 9x squared minus 1, we want, with the minus sign, we want the square root of the thing in front of that to be our hypotenuse. And that means we're going to choose one of these sides to be 1 and the other one to be the radical. I don't know if I did this right or not. So if we do, we want to get x, we want to pair the x with the constant. So that would mean that that's opposite over hypotenuse would be a sine. We want to make it hypotenuse over opposite. That would be a cosecant. But we don't want a cosecant, so I got those in the wrong order. So I'm going to switch those. So we're going to call this side the 1, and this side the square root of 9x squared minus 1. Okay, now we can see that the cosine of theta would be 1 over 3x, which means the secant of theta is going to be 3x over 1, which means that x is going to be 1/3 secant of theta. Then we need to use that to figure out what dx is. So that's going to be 1/3 secant theta tangent theta d theta. We need an expression for our radical. So the square root we want to pair with the constant. So that means that the tangent of theta is going to be the square root of 9x squared minus 1 over 1. So there's our radical. So I think we're ready now to convert this. That 5, I think we can just go ahead and pull that all the way outside. The dx I'm going to put on top. That's going to be a 1/3 secant of theta d theta. The x is going to be 1/3 secant theta, so x squared is going to be the 1/3 secant theta. Oops, hold on there. Squared. I didn't get the dx right. I was looking at x. So it should be the dx should be 1/3 secant theta tangent theta d theta. Okay. then our x squared is going to be the 1/3 secant theta quantity squared, and our radical is going to be a tangent of theta. So let's see, some good things are happening here. We can cancel our tangents. We can cancel one of the 1/3 secant thetas with one of those in the denominator. So that's going to leave us with, let's see, we've got our 5. The 1/3 in the denominator, to divide by 1/3, is going to multiply that by 3. So now we're down to 1 over secant theta d theta, I believe. So that we can call 15. And 1 over secant, since secant is 1 over cosine, that's just cosine theta d theta. Well, that worked out nice. So the integral of cosine is just sine of theta. And then we're going to go back to our triangle and see that the sine of theta is going to be the opposite, which is the square root of 9x squared minus 1 over the hypotenuse, which is 3x. So I guess we can cancel there, and I think our final answer is going to be 5 square root of 9x squared minus 1 all over x plus c. Okay, let's take a look at another one. So on this one, we can draw our triangle again. This time, because we have a sum inside the radical, we know that that is going to be the hypotenuse. And so that means one of these other sides is going to be 3x and the other one is going to be 5. I think this is the way we want to do it. So when we partner our x with our constant, that's going to be tangent of theta is 3x over 5. So that means x is going to be 5/3 tangent theta. So we wanted the x to be a sine, a tangent, or a secant, so we're in good shape. We can now find dx by differentiating this, and that's going to be 5/3 secant squared theta d theta. We need to get the radical, so we're going to partner that with our constant. So adjacent over hypotenuse would be the cosine, so that means the secant of theta is going to be the hypotenuse. That's square root of 9x squared plus 25 all over 5, which means that our radical, the square root of 9x squared plus 25, is going to be 5 secant theta. Okay, so now our integral becomes the dx is going to get replaced by 5/3 secant squared theta d theta, and our radical is going to get replaced by 5 secant theta. So it looks like we can cancel one of, oops, I didn't want to erase it. Let me put that back. So let's cancel one of the secants. We can cancel the 5 with the 5 in the 5/3. We can pull that remaining 1/3 out of the radical, and now it's down to just the integral of secant theta d theta. And we know that one. It's the natural log of the absolute value of secant theta plus tangent theta. So now we're going to go back to our triangle and see that the secant of theta is the square root of 9x squared plus 25 all over 5 plus tangent theta, which is going to be 3x over 5 plus c. Now that would be great. I'd be thrilled with that. Just so you know, you might see this a little differently in the answer in the back. So if we had this, here's the idea behind it. If we had 1/3 natural log And if we wrote that with a common denominator as one big fraction in here, that would be the square root of 9x squared plus 25 plus 3x all over 5. And then you could say, oh, we can use our properties of logarithms. The log of a division is we can subtract the logarithms. So, crazily enough, that would become the natural log of the absolute value of the numerator. So that's going to be our square root of 9x squared plus 25 plus the 3x, and then a minus the natural log of 5 plus c. But the natural log of 5 is just a constant, so we can just lump it together there. And so you might see this written as just 1/3 natural log of the absolute value of the square root of 9x squared plus 25 plus 3x, and be thinking, oh no, I did something wrong because I had 5's in the denominator, but in fact, those are equivalent to each other. And you could also, if you really wanted to, write this 1/3, bring it inside here as a 1/3 power. But I kind of doubt you'll see that in the answers. Okay, let's see if we can do a definite integral. So let's start. This is, again, going to be a trig substitution. So let's draw our triangle. And because we have a square root with a subtraction, what precedes the subtraction is our c squared, our hypotenuse squared. I'm going to call one of these the x and the other one the radical. And let's see, did I do that right? That means that opposite over hypotenuse is the sine of theta is going to be x. That's exactly what I want, because I want x to be a sine, a tangent, or a secant. That is going to make dx be cosine of theta d theta. And our radical, we're going to partner that with our constant. So that's going to be the cosine of theta, adjacent over the hypotenuse. And just for the practice, let's see if we can change our limits to u limits. So that means that if we're right here is where we're going to look. So if we have that 0 is equal to x, that means that theta, sine of what angle would be 0, is going to be 0. And if we say sine of what angle is going to be 1, that's going to be pi over 2. So our limits become 0 to pi over 2. The radical we said was cosine of theta, and the dx we said was also cosine of theta d theta. So we get an integral that's a little bit challenging, cosine squared theta d theta. So this is actually going to require us to do a power reducing formula. Oh boy, let's see. The power reducing formula says that we can make that 1 plus cosine of 2 theta over 2 d theta. So this is going to be the integral. We can pull out that 1/2, going from 0 to pi over 2 of 1 plus cosine of 2 theta d theta. Okay, so we have 1/2 times the integral of 1 with respect to theta is going to be just theta. And if we do a little u substitution in our head there, we're going to get, for the integral of cosine 2 theta, we're going to get 1/2 sine of 2 theta. Now, we need to, I guess we could just go ahead and evaluate this from 0 to pi over 2. Or we have an identity on that one sheet. We could trade in the sine 2 theta for 2 sine theta cosine theta, but I think we can make it work here. Let's see what we can do with this. So we're going to have, I'm going to call that 1/2 theta plus 1/4 sine of 2 theta, and we're going to go from 0 to pi over 2. So plugging in pi over 2, we're going to get 1/2 times pi over 2 is going to be pi over 4, plus 1/4 sine of 2 times pi over 2 is pi, and then we're going to subtract from that 0 plus 1/4 sine of 0. Well, this is pretty nice because we get pi over 4, and the sine of pi is 0, and the sine of, oops, it should have been a 0 here. And the sine of 0 is also 0, so our answer is going to be just pi over 4. Now, if you were really good with your geometry, you could have actually done this geometrically. So just to confirm what we just did there, y equals the square root of 1 minus x squared is actually a semicircle. That's the top half of a circle centered at the origin with radius 1. So its radius is 1. We know the area of a circle is pi r squared, so the area of a semicircle would be 1/2 pi r squared. And so that means that we are going to get that the whole semicircle would be 1/2 pi. And since our integral was just from 0 to 1, we were really going to get just half of that. So that's how we get half of that to be pi over 4. And kind of an interesting little picture to go with that. All right, let's see if we can tackle a partial fraction decomposition problem. So we can say that our integral of 3x plus 4 over the x squared plus 4 is an irreducible quadratic. And so we're going to call that a over 3 minus x, and then plus bx plus c over x squared plus 4. So we're going to multiply through by our least common denominator and see where that is going to take us. So we'll get 3x plus 4 on the left side, and we will get a times x squared plus 4 on the left, and then we'll get bx plus c times 3 minus x. So let's choose first x to be 3 and see where that gets us. So 3 times 3 is 9, plus 4 is 13 on the left. Plugging in 3, we'll get 3 squared is 9, plus 4 is 13a, and everything else gets wiped out, so we know that a is going to be 1. Now it gets tougher because we don't have a really good choice, so let's try maybe 0 for x. So on the left side, we're going to get 4. On the right side, we're going to get 0 squared plus 4 is 4a. So that's going to be 4a plus, the 0 will wipe out the b. And so we're going to get 3c, I believe. And we know that the a is 1. So that's going to get us 4 equals 4 plus 3c. So that means that c is going to be 0. Okay, so then we still got to find b, so maybe a good choice might be x equals 1. So we plug in 1, we'll get 3 plus 4 is 7 on the left side. The a we said was 1 times 1 squared plus 4 is 5, so that's going to be 5, plus the c we said was 0, and so we have b times 1, and then 3 minus 1 is 2. So that looks like if we subtract the 5 from the 7, that's 2 is equal to 2b. So I guess b is going to be 1. So we know our a and our b and our c. So our integral now is going to look like the 1 over 3 minus x. And then, since the b was 1, we'll get just the integral of x over x squared plus 4 dx. So doing a little u substitution in our head, if u is 3 minus x, we're going to get an extra negative sign. So that means we're going to get a negative natural log of 3 minus x in absolute values. And we can do, we can do a little u substitution in our head here, or maybe not even in our head. The du is going to be 2x, and so we are going to get an extra factor of 1/2 out of that. So that's going to become 1/2 the integral of du over u, and so that's going to be 1/2 natural log of our x squared plus 4. So we can write this one of a couple ways. We could say 1/2 natural log of x squared plus 4 minus the natural log of, I guess we better put that one in absolute values, 3 minus x plus c, and that would be fine. We can also flaunt our logarithm skills and bring that up as an exponent, and then because of the subtraction, write it as a single logarithm, the square root of x squared plus 4 over 3 minus x plus c. That's pretty impressive. Okay, so now we're going to move on to our tables. So we can bust those out and see if we can find something that looks like that. So I'm seeing that this looks like it might be number 12. And number 12, let me see what that looks like. That's going to be 1 over u squared times a plus bu. Du is going to be a negative 1 over a times 1 over u plus b over a times the natural log of u over a plus bu, and then plus c. So for us, I think we want the a is going to be the 9, and the b is going to be 3, and the u is going to be x, so the du will be the same as dx. So then I think we get our integral is going to be 1 over, that's going to be u squared, when there's our a plus bu that we want, and it's a good match. So that's going to make our integral be, we want negative 1 over a, so that's going to be a negative 1/9, and we've got 1 over u, which is a 1 over x, plus b over a is going to be 3 over 9, which is 1/3, times the natural log of the absolute value of u, which is our x, over 9 plus 3x, and then plus c. And I think that's going to be our answer. Okay, let's see what we got for the next one. And let's see if we can find a match for this one. And I think we want to use here number 84. So on 84, we have the integral of 1 over 1 plus e to the u du is going to be u minus the natural log of 1 plus e to the u plus c. So we have to, I think, call u equal to 2x squared, which will make du be 4x dx, which is going to make our dx be du over 4x. So if we do that, we're going to get 1 plus, there's our e to the u, and the dx will get replaced by du over 4x. That will allow us to account for that extra x, and we can pull the 1/4 outside the integral. And now I think our integrand is an exact match to what we need. So we're going to get this extra 1/4 times our u, which is 2x squared, minus the natural log of 1 plus e to the 2x squared, and plus c. Okay, very good for that. Okay, let's take a look at this one here. Now, on this one, I don't think we're going to see anything that's a great match with our trig functions. So I think this is going to be our very special substitution. But before I do that, let me take off the limits here. This is going to involve a complication we're not really ready to talk about yet. So our substitution here is going to be that the cosine of theta is going to be, what is the cosine of theta? It's going to be 1 minus u squared over 1 plus u squared. 1 minus u squared over 1 plus u squared. And our d theta is going to be 2 du over 1 plus u squared. So our integral is going to become, I'm going to write it as 1 over 4 minus 3 times our 1 minus u squared over 1 plus u squared times our d theta is going to be 2 du over that 1 plus u squared. So that's going to give us a 2 du in the numerator. Now as we distribute that 1 plus u squared, we're going to get 4 times the 1 plus u squared. And then we'll get a minus 3 times the 1 minus u squared, because that other 1 plus u squared in the denominator will cancel. So that's going to become 2 du over, that's 4 plus u squared minus 3 plus 3u squared. So we have 2 du over, and that's going to be 1 plus 7u squared. So let's see if we can find something in our table of integrals that will match that. And I think it's going to be number 23. So if we pull that 2 outside of the integral, we have du over 1 plus 7u squared. I think this gets really confusing because we've already made a substitution for u, and then we're going to get u's in our formula here. So let's maybe, I'm going to rename this. Let's call this, I don't think we've used x yet, so let's call this dx over 1 plus 7x squared. Okay? So then what we're going to get what we're going to get from here is we want this to be of the form 1 over a squared plus u squared. So we want this to be 1 over a squared plus u squared, and that integral will become 1 over a arctangent of u over a. 1 over a arctangent of u over a. So for us, it looks like the a is going to be 1, and the u is going to be the square root of 7 times x. And so that means our du is going to be a square root of 7 dx. So our dx is going to be du over the square root of 7. So our integral becomes 2 integral of, we have a du over square root of 7, and then we have our 1 plus u squared, which is our a squared plus u squared. So that's going to become 2 over square root of 7, and then we have a 1 over a, which is just 1, and an arctangent of our u over a, which, and our u we said was the square root of 7x, and then a plus c. Okay, I think that's everything we've got here.